So this is a short video lesson on tessellations. Tessellations are included in this unit because of the fact that we're going to kind of use polygons to replicate a pattern. So our tessellation definition is a collection of figures, and those figures can be polygons, that cover a plane, two-dimensional surface, a plane, with no gaps, so gaps are spaces between figures, or overlaps, meaning that none of the figures overlap each other. No gaps or overlaps. Now, a regular tessellation is a specific type of tessellation where the figure that you're using is a regular polygon. So a regular tessellation is a tessellation of congruent, meaning exact same angle measures and side lengths, congruent regular polygons. Now there's other type of tessellations that we'll talk about today, irregular and semi-regular, but for now we'll just kind of look at that key type of tessellation. The sum of the measures of the surrounding a point or a vertex. So when I look at a regular tessellation, the sum of the measures surrounding a single vertex or point must be 360 degrees. Okay? So, with that being said, at any one point, those points make up the vertices, or the number of sides that my polygon includes. So, just as a quick check, if the angle inside the polygon is divisible by 360 degrees, or 360, then it can tessellate regularly. Then it can tessellate. So here we're going to look at a couple figures and we're going to kind of explore and see if these can be regular tessellations. And we're only looking for regular, so that has to fit that 360 feature. So here we're given a figure, a triangle, and it looks like it's going to be an equilateral triangle where all the sides have the same length, and therefore all the interior angles would all be the same. In an equilateral triangle, all the interior angles are all 60 degrees. So when I look at this problem and I go ahead and take 360 and I divide it by 60 degrees, as long as the angle is divisible by 360, which when I divide 360 by 60 I get 6, that means that, yes, this figure can tessellate. So if I would go ahead and kind of redraw that regular triangle at that 600-degree angle, and then I draw another triangle at 60-degree angle, and I draw another triangle, 60-degree angle, another one with 60-degree angle, 60 degree, 60 degree. I can see that that figure repeats over and over again, and it's, again, since it makes a circle, it's going to add up to 360 degrees. So yes, this figure can tessellate. What about a four-sided quadrilateral where all the sides are the same length? Well, since all these are 90 degrees, then yes, if I do 360 divided by 90, as long as this divides out to an integer, like 4, then yes, this is a regular tessellation. Here we have a 1, 2, 3, 4, 5, 6-sided figure, and as long as each interior angle can then be divisible by 360, then I know it tessellates. Last class, or a couple classes ago, we talked about how each individual interior angle of a hexagon can be determined by taking the sum, which in this case would be 720, because 180, 6 sides minus 2 is going to add up to, or multiply to 720, And since there's 6 sides, when I divide that by 6, each interior angle is going to be 120 degrees. So then if 360, it is divisible by that interior angle of 120, which it is, and it multiplies out to 3, divides out to 3, then yes, a hexagon, a regular hexagon, can tessellate regularly. Here we have a 8-sided figure. So we got 1, 2, 3, 4, 5, 6, 7, 8. 8-sided figure. To figure out if this would tessellate, we need to find each interior angle of that octagon. So again, 180 times 8 minus 2. So I'm going to go ahead and put in 180 times 6. I'm just going to multiply out to 1,080. And when I divide that by 8 sides, I'll find each interior angle, which in this case is 135. Once I find that interior angle, I need to see if that interior angle is divisible by 360. So when I divide those two numbers, 360 divided by 135, I end up with 2.6 repeating, or 2.7. Since that's not an integer, that would make 135 not divisible by 360. And therefore, this would not tessellate regularly. Here I have another figure that is a quadrilateral, it's 4-sided, but it's actually called a trapezoid because not all the sides are the same length. This side is a different length than this side. And since it's not a regular polygon, it's not going to tessellate regularly. So it has to be a regular polygon to tessellate regularly. Here we have something that looks similar to what we did in the second example, but here obviously not all sides are the same length. Since this rectangle is not regular, a regular quadrilateral, no, this is not able to tessellate regularly because it's not a regular polygon. So what happens if we can't draw it, but we know that there's 20 sides? So if we know there's 20 sides, we need to first figure out what's the interior angle going to be of a 20-sided figure. We'll assume it will be regular, since they don't give me anything to tell me it's not. So we're going to go ahead and take 20 sides. We're going to subtract 2 from that, multiply it by 180, and divide it by the number of sides. When I plug that in, I end up with a value of 162, meaning that each interior angle of that 20-sided figure is going to be 162 degrees. To check if it tessellates regularly, all I got to do is divide 360 by 162. Since that comes out to a decimal, 2.2, then no, it will not tessellate. Go ahead and try the same process for 10 and 12-sided and see if you come up with the same result. Go ahead and pause the video and try those two on your own. So with the 10-sided figure, each interior angle is going to be 144 degrees. So when I divide 360 by 140, 44, I end up with 2.5, which is not a whole number, so therefore it would not tessellate regularly. 12-sided figure would also be a big no, because 360 divided by 150, the interior angle of a 12-sided figure, comes out to 2.4, which is not a whole number. So, just as a quick recap and help you remember kind of from our examples that we've looked at, the ones that did tessellate correctly were a 6-sided figure, a 4-sided figure, and a 3-sided figure, especially when they were regular. So, no regular polygons with more than 6 sides can be used for a regular tessellation. Okay? And the 3 that we know so far are 3 sides, 4 sides, and 6 sides, as long as they are regular polygons. I challenge you guys to kind of figure out if there are any others out there that exist, just as an experiment. But those 3 are the ones that we're going to have to remember moving forward on testing quizzes. Let's go ahead and jump to this next page. Here we have some other examples of tessellations, which are very common. Sometimes you see this in tile work in bathrooms or in restaurants, or even if you're looking around your classroom at school tomorrow or today, you can see that a lot of the tiles that make up the wall, the cinder blocks, are even though they're rectangles, they actually form a tessellation. It's just not a regular tessellation. So, semi-regular tessellations are formed with two regular polygons. So they're used by taking two regular polygons and they help form this figure. If we kind of zoom in and look at this image, it looks like it's going to be tessellating with two specific types of figures. It looks like it's using a yellow square, and it's also using a 1, 2, 3, 4, 5, 6, 7, 8-sided octagon. So we have an octagon and a square, and when we use those two regular figures and put them next to each other and they share a vertice, like right there, it shares this vertex, those angles end up adding up to 360 and therefore forming a irregular or a semi-regular tessellation. So in this specific example, they're using regular square, or just squares, I guess, because it's a regular quadrilateral, and a regular octagon. And if you remember back, octagons themselves as regular figures do not tessellate regularly, but when I combine them with squares, it does work. So it's important to understand that for semi-regular, the combination of the regular polygons meet at each vertex. So the same combination of regular polygons meet only at each vertex. So if I look at that image more closely, each side of the two polygons meet at an individual vertex every time. So it's not like a side matches up with a vertex matches up with a side. It's always vertex to vertex connections. That's a little different than our regular tessellations, which use irregular polygons. And may be the same shape, or different types of that shape. So for example here, different types. This is technically a rhombus. This can also be worked with rectangles. If you look at the wall in your classroom, we kind of have a figure that tessellates irregularly with the idea of that brick and mortar setup. So it kind of has the same type of principle. So you can see like the rectangles, there's no overlap or anything like that. It's just the same figure used in a different type of setup. So, just as a quick summary of everything that we've talked about here, at each vertex of a tessellation, the sum of the measures of an angle must equal 360 degrees. When the vertex line up exactly at the same vertex points, the interior angles of each of those polygons, they have to add up to 360 or therefore be divisible by 360. Each quadrilateral will tessellate. So any type of quadrilateral that I have can tessellate. Sometimes it's trapezoids with the irregular, like rectangles, or it can be square with a regular tessellation. Combinations of figures can be used to tessellate. That would be a semi-regular tessellation. And only equilateral triangles, squares, and regular hexagons can make regular tessellations. And that's when I have regular figures, meaning all the sides are the same. So here we have some practice problems for you to try from SOL questions. Go ahead and pause the video at this time and go ahead and just try those 3 multiple choice questions. 1, 2, and 3. Once you've attempted those problems, go ahead and unpause the video and walk through the examples for each one. So it looks like here, number 1, when the tiles are tessellated in a plane, what angle measure sum is required to the surrounding for a single point. So again, this is just a basic definition here, but again, we talked about as a single point of a tessellation, the angles of that figure always have to add up to 360, one whole circle. So the correct answer would be C. In number 2, it looks like they have a tiled floor, has a tessellating pattern with two regular polygons. A portion of the tiled floor is shown below. What two regular polygons are used in this tessellation? So again, we have to kind of choose which two. Obviously, the figure that they give me in the middle is a square, because it's a regular quadrilateral, which means that angle is 90 degrees. And since I need to find the other polygon which is attached to that, I need to determine these two angles which are next to that 90-degree angle. And they have to be equal because they're both part of the same regular polygon. So I need to find x and x, and I know this is 90. So really, x plus x is 2x plus 90 degrees. Those two angles have to add up to 360. So when I go ahead then and subtract 90 from 360, I get 270, and when I divide by 2, x is going to equal 135 degrees. So if that's my interior angle here, 135, so this angle is 135, what regular polygon had an interior angle of 135? We're going to go through those steps, right? If that's my interior angle, my exterior angle then would be 180 minus 135, which would be 45 degrees. The exterior angle would be 45 degrees. And since the exterior angles have to add up to 360, I divide 360 by 45. I end up with an 8-sided figure, which would be an octagon. Octagon and square. Let's kind of draw that out to see if that actually works. So I'm drawing this octagon out. Yeah, it kind of does make an 8-sided figure that would look like it would tessellate there. So your correct answer would be F in that case. And last, number 3, some of the angle measures are given for one of the fish-shaped polygons, and they're kind of tough to see, but they're kind of labeled inside there. What was the value of x? And it looks like x is located right here. We're trying to find x. It should be located right here of this angle inside here. So the first thing we're going to want to do is we're going to find other angles in my picture that are the same. So if this guy, of this part of the fish, is 150, that means this angle, which would be the same angle, would also be 150 degrees. The bottom of the fish, this 150, kind of matches the bottom of the fish here, which is also 150. And therefore, if that's 150 and 150, and that's x, then the other side here would also be an x. So to find x, I need to know what 150 plus 150 is, which is 360, or 300, I'm sorry. 150 plus 150 is 300. And 300 plus 2 of the same value is going to add up to a total of 360 because it tessellates regularly, or it tessellates, so it has to add up to 360. So when I subtract 300, I get 60 equals 2x, and when I divide by 2, x is going to equal, by 2, x is going to equal 30 degrees. So my correct answer would be D. So, once you've now completed this video, go ahead and try the practice problems that go with this tessellation notes, and then we will go over those next class.